Okay, welcome to another Orbiter 2010 video. And this video is going to be another installment in this Jupiter moon hopping video series that I'm doing. We're currently on the last hop. We're going from Europa to Io. And in the last video, I spent the time sitting there on Io, or rather on Europa on the landing pad, setting up the plan to get over to Io. We didn't spend a ton of time on it, so it may not be the absolute best plan possible, but I think it's pretty good because we determined that the, let me switch camera views. We determined that the line of nodes was like over here, I believe, and we're arriving here, so we're not technically arriving in plane with Io. So our total delta V is probably, it might be a little bit higher than it has to be, but it shouldn't be by much. Then obviously, you can tell we're not on the ground, we're off the ground. So we got into orbit, and then I set up the orbit eject program. And we can tell in the orbit eject program that we're not going to reach apoapsis, or rather, we're not going to reach the eject point until after we reach apoapsis. So the very next order of business is to warp time forward over to the apoapsis point and then circularize our orbit. So let's do that now. Let's get warp time forward at 100. Let's go to 1,000, speed it up a little bit. You know what we can do too, I believe, since we're crossing a node here, let's, and we were, since I wasn't paying good enough attention when I was getting up into orbit, I was off in my inclination by over a degree. And that's just because I went to the wrong heading, because I don't know what I was looking at. So since we're crossing a node, let's take care of that now. Unfortunately, these boxes, they do mean when it's not filled in, it means one node, and when it is filled in, it means the other. I need to have some paper next to me because I can't ever remember which is which. I seem to recall that what I'm actually going to do, since I don't know, I'm just going to go,
rotation.
Let me bring the vessel to a level position. And it's unfortunate that I didn't do this sooner because we're coming up on the node right now and I need to be doing the burn right now. Okay, so we're level, so if I translate up, no, I need to switch to translation first.
Translation.
If I translate up, okay, that's good. Now I can just use the hover engines. So you can see the EIN coming down. And so if it's not filled in, then it's descending node.
Rotation.
This would not be necessary if I had gone to the correct heading.
Translation.
Okay, let's translate the last little bit there on the EIN. And we'll go with that. It's probably not best to have it exactly at 0, 0 because as we go around, it's going to trend up or down. I don't know which way, but it would be preferable if I left it at like 0.05, like 0.05. That way as I go over to the eject point, it gets lower. But again, I don't know which way it's going to trend. Okay, so once we have our orbit circularized, now we can warp time forward until we are about 1,000 seconds from the time to do the ejection, and then we can set up our IMFD maneuver. Actually, I'm sorry. First thing we need to do is circularize. I forgot that step because I did this. So let's go over to apoapsis. Yeah, you can see it's going farther into the negative, so I should have left it a little bit on the high side. I can probably...
Rotation. Translation.
See if I put in a little bit more translation like that. Maybe out to that number. Then as I go forward, it'll get closer to 0. So there. All right, now we're getting close to apoapsis. Let me bring up orbit MFD because I just like to be able to see... I like to be able to see the APT, and you can't see, you don't get that number in these other MFDs. And we'll go to the prograde position because we're going to be doing a circularization here. And I'll just do it manually. We could use IMFD's circularization, or we could use burn time calculator, but I'll just do it manually. Get a little bit closer to the time to the apoapsis. Okay, back to real time, prograde. And go ahead and start the burn now. That was a little early. Okay.
Rotation. Translation.
And now we have a circular orbit. Now the next order of business is to do the ejection. If you hear any loud screaming types of sound, that's my neighbors. I have got my doors open because it is beautiful here in Florida today, thank God. I'm so sick of winter. And anyway, my neighbors' kids are outside playing, apparently. Apparently they're trying to kill each other. So we're about 1,000 seconds away from the ejection point. That works out pretty well. We can start setting up. our IMFD maneuver now. Now, this part of the plan is one that I found rather confusing for a while, because what we have to do is we have to copy the orbit eject plan over to the delta velocity program, but we can't just bring up the delta velocity program over here, because this side currently is shared with this side. So in other words, the orbit eject program is currently getting its data from here. So if I were to bring up the delta velocity program over here, everything that I've got over here would just vanish like that. So what we actually have to do is we need to bring the orbit eject program up on this side. So we'll go menu, orbit eject. Now you'll note that everything that I have over here matches what I have over here. But since I have it loaded on this side, which is not shared, this side over here actually has the data. So now I can get rid of this, and I won't lose anything. This particular step is one that really tripped me up a lot when I was learning this process, because I just couldn't quite understand what was happening when I would bring up, the delta velocity program on one side, and then I would just lose everything. I'm like, man, what is going on? But if you follow that step, just bring interplanetary MFD up on this side, and we're not going to lose anything because this side is not shared. So it's like this is the master side because it's not shared. So now what we need to do is come to the other side, and we want to unshare it, which, yes, means we're going to lose the data that we have over here, but it's no problem because we now have it over here. So we're going to unshare it. Now we can bring up the course, the delta velocity program in the course menu, and now we can copy this information to this side. First thing I'm going to do is change the projection. And another note, again, check your reference. This will only apply, if you're in orbit around one of those bodies that doesn't have a strong gravitational influence. Although in that case, I don't think we won't follow this exact procedure, so that might not matter. But in general, just make sure your reference is correct, and we're orbiting Europa, so the reference is correct. Let me just tab over to my notes real quick and get caught up with where I'm at right now. Yeah, setting up the delta velocity and map, that's where we're at. Okay, so the first order of business is to set the TEJ to match that closely. It doesn't have to be exact because we're going to change it anyway. So we'll go 1325, enter. And now we're going to go to the delta velocity variables here, and we're going to input them. But remember, this total that we have here is not necessarily all forward velocity, because this is the delta V and this is total. But this might be 600 of forward, it might be 300 of plane change, although it's probably not because our EIN is so low. But it might have some inward and outward, and we just don't know. So the only way we can find out is to press the page button and then bring up the burn vector. And we can see here that we have, it's basically all forward. It's almost all forward. This little bit of plane change is so small that you don't even want to bother putting it in. And that amount of inward and outward is, it's not tiny, but it's small enough that I'm not going to put it in for starters. I'm only going to put it in if I absolutely have to. If it were much larger, like 200 or 300, then I would say, yeah, we probably need it. But in this case, you can see that our total is 1226. And our forward is 1225. So this additional inward outward is only adding 1 meter per second. So if we can get away with it, we're not going to have any inward or outward. So we're going to just set, and we're going to put 12226, and we don't need the decimal point, so enter. And now we are done with the orbit eject program. We have the information that we need from it. So let's bring up the menu, and now we need to bring up the map program, but the map program has to get data from somewhere, and the somewhere it's going to get its data from is going to be the delta velocity program. So we need to share this side now with that side. Now we can bring up map, And I'm going to change the projection. And we want to target Io, which will automatically reference Jupiter. So technically we want to reference Jupiter first, then target Io, but in this case it does it automatically, so that's fine. Now we're going to turn on the display lines, we're going to shut off the auto zoom, we're going to page over, we're going to turn on the sphere of influence, and we're going to turn on the plan. And we can also turn on INT, although I'm not real sure what that does, but it gives us some extra line in there. I guess I'll leave it off because I don't really know what it does. Now we're going to page back over to the main page, and from here we can do our selections, but our selection is currently correct. It's showing us the PE of Io. So with this plan, we're saying that we're going to get to Io and have this as our PEA. So it's amazingly good, actually, without doing any correction. But there's one other thing that we want to do, which I forgot to do in the previous 2 hops, and that is we want to start thinking about our base alignment now. We'll get down to 0.1 for a moment. Yeah, we don't have to do that. We got time. If you're going from Earth to Mars, you don't need to worry about your base alignment when you're at Earth, because there's so much distance to cover that the base alignment just doesn't matter until you get farther out and you want to start doing mid-course corrections. But when you're doing these moon hops, when you're going from one moon to another, the distance that you're going is quite short. I mean, we're not going that far, really. So we want to think about our base alignment before we ever do the ejection. So we're going to go to the menu, we're going to go to configuration, and we're going to go to the landing target. And Io by default doesn't have any bases, but I've added bases to all the moons of Jupiter and all the moons of... I added bases to all the moons of the outer planets, and I put those bases up on Orbit Hanger. So I'll be sure to include links to that in the description below. So the bases I made, each one is just called the body name base. So Io base, Europa base, Ganymede base, very simple. So set Io base is our target. Now we'll come back to the menu, go to the map, and from here, first of all, let's work on this PEA a little bit, because as we're moving forward, it's getting a little bit worse. So we want to start by adjusting the time, actually, because if we can just adjust time, then we don't have to make any changes at all to our velocity. So let's see what we can do with just time at 1x. Make sure it's 1x. And by taking out a little bit of time, it's making things worse. So that would invariably mean that adding in time would make things better, and it is. And you can see that we didn't even need that inward or outward. It's when you have inward and outward, you're burning off center from the flight path. It's inefficient. So if we don't have to have it, then we would prefer not to use it. Clearly, this is trending up quite quickly. So obviously, the best thing to do here is going to be to put the PEA well below the surface. Now, when we're all said and done, when we're just about ready to do the burn, we really don't want the PEA to be that far below the surface. When you're going from Earth to Mars or the other planets, we tend to put the PEA well below the surface, like all the way to the center of the planet. But I've found that when you go from moon to moon, erroring that far down is not necessary. In fact, not only is it not necessary, it's not efficient, because you'll end up having to then re-raise the PEA by a significant amount. So I would say basically we want the PEA to be right at the surface, or even, maybe 50 kilometers below the surface or 100 kilometers below the surface, but no more. We definitely don't want to be 2,000 kilometers below the surface. But we can see that this is, trending up as we go forward, so we'll keep an eye on that. So by the time we get to TEJ 200 seconds, this might have climbed back out to 1,000 or something, so we'll pay attention to that. But for now, I want to see what my base alignment's going to be like. So I'm going to press Mod, and I can see here that Io base, if I fly this plan as is, I'm going to have a 46-degree angle and climbing to the base. That's quite significant. That's not going to work. In other words, we're not going to arrive at Io and be in plane with the base. We would be off by a significant amount. So we're gonna work on that here as well. Let me take a sip of my drink. I've noticed that this microphone is so sensitive that you can actually hear me drinking when I take a sip. It's like gulp, gulp. I also hate the fact that when I breathe in, it picks up. So I don't know what to do about that. I've done a little bit of research online, but I don't know what to do about it. The mic is just too good, I guess. I really wish I could cut out the breathing, but I just don't know how to do it. I thought about like putting it farther away, but then I'd have to like scream or something, and I don't want to talk loud because it would make my voice hurt. Anyway, let's work on our stuff here. So in addition to working on the PEA, we need to work on the angle. So let's see what taking time away does. That's making it worse, so that's fine. That's actually good. So if we add in some time, it's making the angle way better. But it's now we're bringing the PEA up. So what we'll do here is we'll just bring the angle down to like 1 degree or something, or maybe not that far, maybe like here, 4 degrees. But now we've got a PEA that's actually not too bad because it's high, but it's coming down, and that's continuing to go up. So we need to bring the angle down below 0. So let's continue to add in time. Like that. So now we're below, the angle's negative, but it's getting closer to 0. But now let's see what we can do about the PEA just with a little bit of a little bit of prograde. So if I add in a little bit of prograde, it's bringing the PEA down, and it's having just a tiny effect on the angle. So that's good. Let's do that. And we're not really adding in that much more velocity because this is at 1x. So I don't remember what the original number was, 1.2, but we're only up to 1.30 now. Okay, let's see though if, let me take some of that back out. I think we were at like that number originally. So let's see if a little bit of plane change will help us bring the angle down and bring the PEA down. So let's go to 10x. Anytime you do plane change or inward outward, typically 10x is better, but just make sure you put it back to 1x before you adjust time and forward. Okay, 10x. So a little bit of plane change in this direction is not helping either one of them. So if anything, we want to go the other direction. It's bringing the PEA down, but and watch the total too, because you'll notice again because of the way the equation works. 20 additional delta V doesn't add, or rather I should say 20 additional delta V of plane change doesn't just automatically add 20 more to the total. You can see the total hasn't changed. So that's why it can be cheaper to just use one of these other variables instead of just relying strictly on the prograde. And now it's gone up by 1 meter per second. We've added almost 40 worth of plane change. That's quite a bit of plane change though, so I don't know if I really want to do this, but what I'm going to do is I'm going to get the numbers where I want them, and then we're going to warp time forward a little bit farther. We're going to get a little bit closer to the eject point. So we've raised our total delta V now by 6. All right, let's get a little bit closer. The PEA is 500, but it's going down. The angles, let's actually get the angle a little bit lower. All right, let's get to 500 seconds and see how things look. Okay, now we're below the surface and kind of continuing to go down, but now our angle's way out. So let's see what happens here. So let's take out some of this. That's too much. You can see as we're getting closer to the time to do the ejection, we don't need that much plane change for the off base distance, but now our PEA is going way up, so we'll have to address that. Okay, so basically we can just reset the plane change for now because it's really not doing anything for us. Let's check time and prograde again with regards to the PEA, and we'll just watch that angle to the base here. So again, adjustment down to 1x, and adding in time's not helping, so let's take out time. It's raising the angle quite a bit, but we'll address that here in a moment. So now that we're down to 1,000 kilometers on the PEA, let's see if just prograde can do anything for the, yep, prograde's helping on the angle a little bit. So I think what we can do here, if we take out some prograde, which actually saves us a little bit of delta V, so that's good. Take out a little bit more. But then we add in time. Or was it take away time? I don't remember. Okay, add in a little bit of time. It's bringing the angle down. Okay, so let's overshoot on the angle. Bring it way down to like -10. PA is getting very far out though. So, but now if we take away prograde, now it's making the angle worse. So we're adding in a bit of prograde that's helping both of them a little bit. Okay, we're definitely going to have some kind of inward-outward. All right, let's go with that. And let's come to the inward-outward. And it looks like negative outward, that's bringing the PEA down, it's raising the angle. Okay, but we're still not too far away from that 1226 figure that we had originally. Okay, let's go with that on the PEA for now, and let's adjust prograde. I know I'm at 10x, but I just want to see. So taking out some prograde is bringing the PEA down, and it's actually now it's taking it up. Okay, I gotta think about this. It does get a little confusing sometimes as to what is the right move. So adding in a little bit of DVI, it's bringing the angle down. I guess I probably need plane change then, not inward outward. So positive plane change. And this is why you want to you want to start thinking about this early, because you can tell. Let me actually page over here and turn on the burn vector now. That way when I get to 180 seconds, it'll orient the vessel, but I've still got work to do here because I don't want a PEA that high. That's ridiculous. So I'm going to bring down the PEA. That's more important. Okay. And I need to do some time adjustment here too, I think. Oh boy, I'm running out of time and I'm not sure what to do. I'm not sure what the best course of action is. I just need more time to set this up. Man, I can't believe I need that much plane change. 75 degrees, that's almost perpendicular to the base. I don't want to burn this maneuver. I may have to use the scenario editor, back time up a little bit. That's just... I'm going to have to give myself more time. I don't want to burn a really, really bad maneuver, so let me back up by like 5 minutes. Okay, let's try this again, now that we've got a little more time, so we're not so pressured to figure this out. I hate doing that because it just totally blows the immersion and blows the, blows the idea of doing the flight right, but we're learning, so it's cool. So adding in prograde, taking away progrades, helping to a point. I'm going to focus first of all on getting that PEA back down. So taking away prograde and then taking away time. is bringing the PA down. Okay, if I have to have a PA of like 500 or 800, that's fine. But that off base distance is terrible. There's got to be a way to resolve that without using just a ridiculous amount of plane change. Okay, so, but it's only, but again, it's not that much delta V, because you can see 33, and we're only up to 34. Okay, now PA. This is so irritating. Adding in just a little bit more delta V to drive down the PEA is... Alright, let's do this. Inward, outward has to be what we need. So inward's bringing the PA down a little. There's always a way to fix this, by the way. Don't ever think that you can't find a right solution. There's always a right solution. It's just a matter of finding it. All right, let's do that. Oh my gosh. Making things worse and worse. I may just have to skip the base alignment and do it as part of the mid-course correction. Yeah, unfortunately I'm just going to do that. So I'm going to reset the plane change and reset the inward outward and just work on, just have a low PEA. And then we'll have to worry about the mid-course, we'll have to worry about aligning with the base as part of the mid-course correction. All right, so just a little bit of an adjustment on the time to bring the PEA down. Okay, that's the wrong way. And that's the wrong way. So a little bit more on the time. And it looks like we need less delta V. This is apparently the hardest hop that I've done. The other ones seemed like they were much smoother than this one. All right, let's find the lowest number. Eight, 7. So we're going to bring it all the way down and then overshoot a little bit and then adjust time slightly. Okay, now a little bit more. We're coming right up to the burn, so I'm really pushing things here, but... Okay, so keep going, overshoot a little bit. Actually, it's fine just like that. Okay, there we go. At least we got our PEA about where we want. The base alignment's unfortunate that it's that far off, but sometimes it's a little tricky to get things set up exactly how you want. So we're going to go ahead and do this berm. We're going to be, you know, at almost a 45-degree angle to the base. So we'll just have to remember that probably like as we get out of Jupiter, as we get out of Europa's strong SOI, then we're going to want to start immediately thinking about base alignment. Let's go ahead and warp time forward. And as soon as this burn's done, we'll go ahead and end this part of the video. Page over here to bring up the burn vector just to see how things are coming along. Page over here, turn off the plan so that we can see things in real time. Turn on translation, which it's already on. The burn's complete. Yeah, I guess it's done. Yeah, it's complete. Now we want to check our PEA. It still shows that it's negative 76, so we don't need to make any corrections there. That's good. All right, so that's going to wrap it up for this part of the video. And when we come back, we will warp time forward. We don't have very far to go. PET, let's see, it's only 99,000, so it's only a little over a day to go from Europa to Io in a Hammond transfer. So it'll be a pretty quick flight. And we'll take care of that when we get back, and we'll do the base alignment and hopefully, get lined up without a huge delta V cost. If you like this part of the video, like it. And if you didn't like it, don't like it. And leave comments down below if you would, please. I always like to read your comments and thoughts. And if you saw some things that I did here that could be done better, or if you have other ideas, leave those thoughts below. I'll read over it. Check for links in the description down below. I will see you in the next part. Go,
Rotation.
let me bring the vessel to a level position. And it's unfortunate that I didn't do this sooner because we're coming up on the node right now and I need to be doing the burn right now. Okay, so we're level, so if I translate up, no, I need to switch to translation first.
Translation.
If I translate up, okay, that's good. Now I can just use the hover engines. So you can see the EIN coming down. And so if it's not filled in, then it's descending node.
Rotation.
This would not be necessary if I had gone to the correct heading.
Translation.
Okay, let's translate the last little bit there on the EIN. And we'll go with that. It's probably not best. Then as I go forward, it'll get closer to 0. So there. All right, now we're getting close to apoapsis. Let me bring up Orbit MFD because I just like to be able to see. I like to be able to see the APT, and you can't see. You don't get that number in these other MFDs. And we'll go to the prograde position because we're going to be doing a circularization here. And I'll just do it manually. We could use IMFD's circularization, or we could use burn time calculator, but I'll just do it manually. Get a little bit closer to the time to the apoapsis. Okay, back to real time, prograde. And go ahead and start the burn now. That was a little early. Okay.
Rotation. Translation.
And now, okay, welcome to another Orbiter 2010 video. And this video is going to be another installment in this Jupiter moon hopping video series that I'm doing. We're currently on the last hop. We're going from Europa to Io. And in the last video, I spent the time sitting there on Io, or rather on Europa on the landing pad, setting up the plan to get over to Io. We didn't spend a ton of time on it, so it may not be the absolute best plan possible, but I think it's pretty good because we determined that the, let me switch camera views. We determined that the line of nodes was like over here, I believe, and we're arriving here, so we're not technically arriving in plane with Io. So our total delta V is probably, it might be a little bit higher than it has to be, but it shouldn't be by much. Then obviously, you can tell we're not on the ground, we're off the ground. So we got into orbit, and then I set up the orbit eject program. And we can tell in the orbit eject program that we're not going to reach apoapsis to have it exactly at 0, 0, because as we go around, it's going to trend up or down. I don't know which way, but it would be preferable if I left it at like 0.05, like 0.05. That way, as I go over to the eject point, it gets lower. But again, I don't know which way it's going to trend. Okay, so once we have our orbit circularized, now we can warp time forward until we are about 1,000 seconds from the time to do the ejection, and then we can set up our IMFD maneuver. Actually, I'm sorry. First thing we need to do is circularize. I forgot that step because I did this. So let's go over to apoapsis. Yeah, you can see it's going farther into the negative, so I should have left it a little bit on the high side. I can probably...
Rotation. Translation.
See if I put in a little bit more translation like that. Maybe out to that number. Or rather, we're not going to reach the eject point until after we reach apoapsis. So the very next order of business is to warp time forward over to the apoapsis point and then circularize our orbit. So let's do that now. Let's get warp time forward at 100. Let's go to 1,000, speed it up a little bit. You know what we can do too, I believe, since we're crossing a node here, let's, and we were, since I wasn't paying good enough attention when I was getting up into orbit, I was off in my inclination by over a degree. And that's just because I went to the wrong heading because I don't know what I was looking at. So since we're crossing a node, let's take care of that now. Unfortunately, these boxes, they do mean when it's not filled in, it means one node, and when it is filled in, it means the other. I need to have some paper next to me because I can't ever remember which is which. I seem to recall that what I'm actually going to do, since I don't know, I'm just going to